Here's a secret about physics problems. The hardest part usually isn't the algebra. It's the very first step, deciding what you're looking at and which pushes and pulls actually matter. Get that right, and the equations almost write themselves. This is the art of the free body diagram. Everything begins with a choice. Before we can describe any forces, we must decide precisely which objects we care about. That chosen collection is our system. Often the system is a single isolated object, one block, one planet. But it can just as easily be several objects grouped together and treated as one. Nothing counts as a force until we've drawn the boundary that says what's inside the system and what's outside. Once the system is fixed, we add up everything acting on it. Force is a vector, so we can't simply add magnitudes. We add arrows, tip to tail, respecting direction. The total force on the system is the vector sum of the individual forces. F equals F1 plus F2 and so on for every force present. That single resultant arrow is exactly what Newton's second law responds to. The free body diagram is how we picture that sum. We shrink the entire system down to a single large dot, a point. Later in the course, you'll see this point is really the center of mass, but for now, it's simply where all the forces live. From that dot, we draw one arrow for each force acting on the system, pointing in the direction the force pushes or pulls. Longer arrows mean stronger forces, and crucially, we draw only the forces acting on the system, never the forces the system exerts on everything else. Which arrows might you draw? The regular cast includes contact forces, tension in ropes, gravitation, friction, pressure forces, spring forces, and electric and magnetic forces. We'll meet each one as we go. Sometimes, instead of gathering every arrow at one dot, we draw each force right at the spot on the object where it actually acts. When we do that, the system is no longer a single point. It becomes an extended picture of the real object, with forces placed where they truly apply. To turn this picture into numbers, we lay down coordinate axes. With a Cartesian system chosen, we resolve the total force into components. Its x component along I hat, its y component along j hat, and its z component along k hat. And here's the useful part. Each component is itself a simple sum. The x component of the total force is just the x component of the first force plus the x component of the second, and so on. The diagram does the bookkeeping. Read each arrow's shadow onto each axis, then add them up. Now the deepest challenge in all of mechanics. Writing down forces is easy once you know them. The real difficulty is building the physical model, deciding out of every conceivable influence which forces to actually include. Include too few and your prediction comes out wrong. Include too many and the mathematics becomes impossible. Good physics lives in that judgment, knowing what matters and what you can safely leave out. Consider the planets. For almost all planetary motion, a single force law, Newton's universal law of gravitation, was enough to predict the orbits with stunning accuracy. But there was an anomaly. Mercury's orbit slowly shifts in a way Newton's law couldn't quite explain. Anomalies like these are precious because they can point to new physics. Einstein corrected Newton's law of gravitation with general relativity, and one of its very first triumphs was predicting exactly this drift, the perihelion precession of Mercury. Yet not every anomaly means new physics. Sometimes it's just a complication from ordinary, well-understood forces that happen to be hard to model. Friction is the classic example of that judgment. Whenever objects move, some friction is always present. The only question is whether to keep it in the model. Air resistance is often dropped because its mathematics is genuinely messy, even though it can dramatically change how something moves. Surface friction between two solids is a different story. Sometimes we ignore it, but often we shouldn't, and we usually can afford to keep it, because its formula is simple enough to include without making the problem impossible to solve. So here's the working recipe. Start with the simplest model that could possibly capture the situation, deliberately leaving out the small effects. Test its predictions against reality. If they hold, you were on the right track and you can layer in the final forces one at a time. If they don't, you've learned exactly where your picture was too simple. Define the system, draw the forces, decide what matters. That discipline sequence is how every hard problem in mechanics gets tamed. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.